In this video, I'll show you how to find the inverse of a matrix in general, not just a 2 by 2 matrix, but a general n by n matrix. So first of all, why do we care so much about the matrix inverse? It turns out the matrix inverse can be used to help us solve systems of linear equations. Here's an example. Suppose we wanted to solve this system of equations, x1 plus 2x2 equals 1, and 3x1 plus 4x2 equals 3. Of course, we already know ways to solve such systems, but I'll show you another way now. Let A be the coefficient matrix of the system. So this 1, this 2, this 3, and this 4. So A is the matrix 1, 2, 3, 4, and B is the right-hand side vector, the 1, 3. Then the system can be written as A times x equals B, where x is simply the vector whose components are x1 and x2. We've already seen that the matrix A is invertible, and we found its inverse as negative 1/2 times the matrix 4, negative 2, negative 3, 1. Now, since we have that AX is equal to B, if I multiply both sides of this equation from the left by A inverse, what do I get? Well, A inverse times A is the identity matrix, and the identity matrix times X is simply equal to X. So I have found X as A inverse times B. Here again it is in more detail. X is the same as A inverse times A times X, because A inverse times A is the identity matrix. Because matrix multiplication is associative, I can move these parentheses to a new location, namely around A times X. And A times X is equal to B. That's what we're requiring. And so this equals A inverse times B. But I know what A inverse is. I know what B is, and so I can do this out. And I find out this is equal to 1, 0. But remember that X is simply the vector x1, x2. And x1 and x2 are the two numbers we're actually looking for. And so x1 needs to be 1 and x2 needs to be 0. And that's the solution to my system of linear equations. So if I take the coefficient matrix of the system of linear equations, invert it, and multiply it with the right-hand side, that solves my system of linear equations. Let me quickly point out that this is numerically not a very efficient way of finding the solution to a system of linear equations, but nonetheless, it's very useful. And therefore, in general, you see that if A is an invertible n by n matrix, then for any right-hand side B, the system of linear equations AX equals B has a solution, and I can find it as X equals A inverse times B. We already know how to find the inverses of 2 by 2 matrices, but how do I find the inverse of an n by n matrix? There's actually an algorithm, and here it is. You place A and the identity matrix IN side by side to form the augmented matrix A and IN. Just like we did for solving systems of linear equations, we wrote down the matrix A and the right-hand side. This time, we're sort of writing down a much larger right-hand side, namely the whole identity matrix. Then you perform elementary row operations on this augmented matrix with the goal of bringing A into reduced row echelon form. If it is possible to row reduce A to the identity matrix, then A is invertible, and the same operations performed on the identity matrix, which is on the right, will transform this identity matrix to A inverse. If it's not possible to row reduce A to the identity matrix, well then A is actually not invertible. This is probably best understood with an example. Suppose we wanted to find out whether the matrix A given right here has an inverse, and if it does have an inverse, find its inverse. So what do we have to do? First step is to write down the identity matrix next to A. So there it is. Here's A, and there's the identity matrix. My goal is to perform elementary row operations on A to bring A into the identity matrix and perform the exact same row operations on this identity matrix right here. So what's the first thing we do? First of all, we want to create a 0 right there by taking the third row and subtracting from it 3 times the first row. I've done that exactly right here. So that gives me this 0 and a 3 and a negative 8. And here I have 0 minus 3 times 1, so that gets me this negative 3 and so forth. I've also divided the second row by 2 to make this 2 into a 1. My next goal is to get rid of this 3 right here and make that 3 into a 0. So I take the third row and subtract from it 3 times the second row. This gives me a 0 in this position, and -8 minus 3 times -3, so that's -8 plus 9, that gives me this 1, and similarly over here. So now I have a matrix in row echelon form, but I also want to produce zeros all the way up here. First of all, I'm going to use this 1 to create a 0 in this position right here. So I'm going to subtract the second row from the first row next. When I subtract the second row from the first row, I create a 0 right here, and I have 1 minus -3, which is 1 plus 3, which gives me this 4, and so forth. Finally, I'd like to create zeros here and here, and I do that by using this last row. So I add 3 times the last row to the second row to create a 0 here, and I subtract 4 times the last row from the first row to create the 0 right here. And this is what I end up with. I perform the exact same operations on the right-hand side. And by doing so, the left-hand side got transformed to the identity matrix, which tells me the matrix A was invertible. And more than that, this matrix that is now showing up here on the right-hand side, that's the matrix A inverse. And we can actually check that A times A inverse is indeed A inverse times A, and is I3, the identity matrix. Here are a few useful facts about invertible matrices. If A is an invertible matrix, then the inverse is also invertible. And just like for numbers, the inverse of the inverse is A itself. Furthermore, if you have 2 invertible n by n matrices, then the product is also invertible, and the inverse of the product is the product of the inverses, but in the reverse order. So A times B inverse is B inverse times A inverse. This should remind you a little bit about the transpose. We had something similar happening for the transpose. When we looked at the transpose, we had the transpose of the product is the product of the 2 transposes, but in the opposite order. The same is true for matrix multiplication. That's very important to remember. Finally, if A is an invertible matrix, then the transpose is also invertible, and it doesn't matter whether you transpose first and then invert, or invert first and then transpose. So let's look at some examples. Let's look at these matrices A and B right here, and I also wrote down their inverses that we found earlier. So you have A inverse and there's B inverse. Suppose you wanted to find the inverse of A inverse. A inverse is right here. So you wanted to invert that matrix right there. Well, instead of doing so, we know the inverse of the inverse is simply A. So I don't have to do anything. That's simply the matrix A. Also, the inverse of the product AB. If you multiply A and B with each other, you get this matrix that I wrote down right here. You can check that if you want. And if I wanted to find the inverse of that, I don't have to think hard at all, because I know it's the inverse of B times the inverse of A. So I take this matrix and multiply it with this matrix right there. So there it is, the inverse of B and the inverse of A. When you multiply that out, you get this matrix right here. And finally, the inverse of A transpose. Well, here's A transpose. You take the matrix A and you find the transpose by just swapping out these 2 elements right there. If I wanted to find the inverse of this matrix, rather than finding that by hand, I could simply take the inverse of A first and then transpose the result. But the inverse of A is right here, so I simply need to transpose this inverse of A. So there's the inverse of A. And now I need to transpose that, so in this 2 by 2 matrix case, I'm just swapping out those 2 elements, and I have the inverse of A transpose. So now you know how to find the inverse of a more general n by n matrix A, how to decide whether an n by n matrix A is invertible, and you even know a few facts about invertible matrices.